Let's start off. Let's look at the practice test is up. I just picked, I think, 5 problems from the practice test, and then there's one from the Unit 5 test number 1 that I want to go through also if we have time. These are all pretty representative though. Let's take a look at one like this where they're wanting us to find a difference, right? So what are the steps we got to do to simplify this difference and come up with a simplified answer as a rational function? What's the first thing we got to do, Tyler?
Factor out the x.
Okay, so yeah, we want to factor everything. Really would be nice, right? But especially the bottom. We've got to find the least common denominator. So we'll take the bottom. Let's take this first fraction. That'll be our yellow fraction. We're going to go ahead and factor that out. So what does the bottom factor into?
X plus 4.
Okay, good. It's difference of squares. So x plus 4, x minus 4. And then minus, and then this guy's already taken care of, isn't it? It's already factored. Okay, so what's our least common denominator going to be then? Okay, well, if we were to expand it out, it'd be x squared minus 16. Let's go ahead and leave it in factored form. We need the smallest list of factors that will include those two and also include that one, right? And so that's just going to be x plus 4 times x minus 4. And so remember how we think about this. Now let's compare this just real quickly. Let's compare this to something like that, right? What do we do here? What's our common denominator? Let me change this just a little bit. I'll do one minor tweak to this, just to remind us how this all works. How about that? Okay, so what's our common denominator in this case? 3/10 plus 1/6. 30. All right. So, and you with numbers, it's no big deal. Probably what you do in your head is you just look at the smallest common multiple. You think of a list of multiples and find the first one that overlaps, right? We could also, if we were to think about this in terms of factors, what are the prime factors of 10? Okay, 5 and 2. Prime factors of 6. Okay, 2 and 3. And so then our least common denominator, we know it's 30. How do we get that from the factors? Well, we want the smallest multiple of all of those factors, right? So we want the smallest number that's going to include both the factors 2 and 5 and the factors 2 and 3. Well, what's that going to be? 2 times 5 times 3. We've got a common factor, so that only has to show up once, right? Okay, same kind of thing up here, right? So if we were to add this up, in order to get the common denominator of 30, what would you multiply this fraction by? The bottom. Focus on the bottom. What do you need to multiply the bottom by? 3. Got to do the same thing to the top, right? And then over here, you'd multiply the bottom by 5. Do the same thing to the top. It's the same thinking up here, isn't it? If we want to get the common denominator, x plus 4 times x minus 4, this guy's done, right? But what do I need to multiply this other fraction by? Yeah, I need an x plus 4 on the bottom. So I'll multiply top and bottom by x plus 4, right? And from there, it's all pretty much downhill, right? We know that from there we get our common denominator on the bottom of x plus 4 times x minus 4. And then when we add or subtract fractions, we just add or subtract the numerators, right? And we found our common denominator, and so then we would just have to take all this part right here and simplify that, right? What's that give us? Negative 4. If I were to expand this out and distribute the negative sign, you can do that in your head. You guys are smart. What's that going to be? we're gonna get minus x squared, good. Then we get a plus x, good. And then a plus 20, very good. Okay, and so if I combined all that stuff, what's my final answer look like? Negative x squared plus x plus 16 over x squared minus 16. Okay. Now notice on this from the study guide or the practice test. Notice on here I didn't actually tell you that p of x and q of x had to be expanded out. So if you want to leave the bottom, the denominator, for example, in factored form, you can. It's fine. Okay. That'll cut out a little bit of work for you. All right. So questions on that? All right. Let's look at one like this. Quotient. Okay, what do I do if I'm dividing rational expressions? What do I always do if I divide by a fraction? Flip and multiply. Good. Okay, so we'll write this then as, let's go ahead and factor it while we're doing that. What's the top factor into of the first fraction? Let's make this the yellow one.
3 times x minus 2.
Okay, so we can take out a 3. We always want to try to factor out a GCF if we can. On the bottom, what magic numbers do we get?
X minus 2, x minus 6.
Okay, x minus 2, x minus 6, good. And then we're going to multiply by the reciprocal of this guy. So then what ends up on the bottom?
X plus 6, x minus
Okay, good. We'll factor, it's a difference of squares. X plus 6, x minus 6. Then on the top we get this guy. How does that factor?
Minus squared.
Good, I can pull out a 5x squared, leaving what? X plus 6. Okay, good. So there we are, right? What can we do if we're just trying to write a simplified polynomial? What can we do at this point if we're multiplying? We can't do this if we're adding or subtracting, but if we're multiplying, what can we do? Yep.
I got one.
Yeah.
Where did you get x plus 6 and all parentheses on the top? Green?
Oh, it should be minus, shouldn't it? Yep, you're right. Thank you.
I don't know where you got it from.
No,
I-
it's plus.
It is plus? Oh, it is, yeah.
I'm not saying it's wrong, I just don't know how you got it.
It's from the bottom. We just factored out. It's a binomial, right? So we can't break this apart like we would a trinomial, right? There's no magic numbers or anything. But with a binomial, at the very least, we want to see if we can factor something out. So the greatest common factor would just be a 5x squared. Does that make sense?
Yeah.
Okay. So then next step would be cancel like factors, right? And because we're multiplying, we can do that, right? How come that is? Let's just take a second and don't just remember that you can. Think about why you can. When you multiply, you just multiply straight across, right? So we don't even really need that multiplication sign there, do we? We could just extend the bar if we wanted to, and it's the same thing, right? So then everything on the top of either yellow or green fraction is on the top or bottom of the product of the whole, right? So we could do, let's see, we could do that. What else could we do? Plus 6, like so. And then we would just multiply straight across and see what we get. Actually, we can just leave it like that. We don't have to, once again, we don't have to factor this. Or, expand it. We can leave it in factored form. So what would we get? 3 times 5, 15, x squared over x minus 6 squared. We could just leave it like that. Okay? Make sense? Rather than, I put a similar question on the review later, but it's the same kind of thing. What I did there were a few difficulties with these problems, I'm sure you remember. So I rewrote all these so that I separated out the parts so that you could do you could actually find the quotient in one problem, and then it would allow you to not have to multiply everything out. You could leave it in factored form. It would recognize that and mark it right. As a separate problem later on in the test, or on the review today, we'd see one where it would say, okay, what's the domain? In other words, what are the restricted values, right? So let's just go ahead and do that one now, because we've done a little bit of work on this. What values of x would we have to restrict?
2.
Okay, so we'd have to say x cannot equal 2. What else? X cannot equal 6, is that it?
Negative 6.
Ah, it's not, is it? Okay. X cannot equal negative 6, how come?
Because that's only one.
Okay, because it's in the denominator before we simplify, right? And anything, remember the rule on this one. Any factor that appears in the denominator at any point during the process has to be an excluded x value, right? Because you can never divide by 0, right? So this guy comes from that factor, this guy comes from that factor or that factor. That guy comes from that factor. We done?
And then there's the 0.
Ah, there's the 0. How come?
Because that was on the side.
Okay, because up here in this first step, right, we combined a couple steps, but maybe we shouldn't have. If we were to take this fraction as it's written right now before we flip and multiply and factor that out, in the denominator we got our 5x times x plus 6, right? And that gives us a 0 in the denominator of x equals 0, right? Do you see that? So even though we never actually used this fraction, we flipped it and then multiplied. The fact that we were dividing by this function, right? This expression means that we have to even include the zeros of the denominator before we flip and multiply. Does that make sense? So that counts as a step. That's what we started off with. So we have to look and see what are our original zeros of the denominators. Okay, so we got another one. Goes clear back up to there. Okay? Questions? All right? Good, good. Okay, we just did that one. Okay, how about this? Okay, this is the stuff from 5.3. Okay, I did put up an extra 3 problems on 5.3, and that's it for, or I mean 9.3, not 5.3. I'm saying 5.3, 9.3. That's it though. This will be it for the Unit 5. What do we do with something like this when we're trying to solve a rational? We call this a rational equation. It's an equation involving rational expressions. What do we do? Clear, yeah, really all we're doing is clearing fractions, isn't it? Right? Same way we would with numbers. We want to figure out what the least common denominator would be, the least common multiple of all the denominators, and we'll multiply through by that to clear all the fractions. Okay, so what is, in this case, and let's go ahead and do it in factored form, what is our least common denominator? If I were to factor this one, what would the factors be? X minus 6, x plus 4, right? So then what's our least common, Matthew, what's our least common denominator? Product of what factors?
X minus 6, x minus 4.
X minus 6, x minus 4, good. Perfect, okay, so that's what we're gonna multiply everything by, right? We're gonna multiply through top and bottom by that. So, I guess I should show that. So we've got, I'm gonna go ahead and write this in factored form. So technically we do this, don't we? We're going to distribute that through both sides. Okay, when we do that, what happens? Right, we always want to remember when we're clearing fractions, and this goes back to the very beginning of the year. Remember the trick I showed you guys? You know that when you're multiplying through by the least common multiple of the denominators, the least common denominator, you're guaranteed that you're going to be able to cancel stuff, right? That's the whole point, is we're canceling denominators. That's what clearing the fractions means, right? So we'll always reduce first and then distribute, right? So when we take this LCD and we distribute it to the first fraction, well, everything cancels, doesn't it? Right? Remember, we just end up getting, we used to write the number up here and then point it down at the top to show that that's what we're multiplying the numerator by. So this first term on the left side just becomes what? -2. Okay, what about here? If I multiply this guy times the second fraction, what's gonna cancel? Yeah, the x minus 6's, right, will cancel, leaving us with an x minus 4, right? So we end up with plus 2 times x minus 4 equals, and then what about over here? Here I'd get those canceling. And so I'd get x minus 5 times x minus 6. Another way of thinking about that is, just think about the only part that's not included in the denominator already, and know that you're gonna have to essentially be multiplying top and bottom by that, right? Does that make sense? So you know that because we're missing an x minus 4, that's what I'm gonna multiply the top by, right? Because we're missing an x minus 6, that's what gets multiplied through by the numerator, okay? Now what? Say it again? Distribute, and we're gonna put it in what form? I think I heard it. What do we call that when we want to solve any equation? We got to put it in what form? Standard form, set it equal to 0, so we can factor it and apply the zero product property, right? So let's do that. So let's see over here, let's go ahead and distribute and combine like terms, and we get what? 2x minus 8 minus 2 is 2x minus 10. And then what about over here? You guys tell me, what do we get?
X
Minus, okay, and so if I push everything to one side, we take these two terms and push them to that side, right? We end up with an x squared. If we subtract another 2x minus 13x, add 10. So there's the equation that we get, right? Okay, so what do we do? Factor. This is one, if we couldn't factor, we'd use the quadratic formula, right? But we can factor. What are our magic numbers? Be careful about signs. What are the magic numbers? -5, -8. So we end up with the solutions. X equals 5, or x equals 8. Are we done?
Never.
Maybe, but we don't know, right? We have to check something. What did we not do? We'll have to go back and do. Yeah, we gotta look for excluded values. Well, what are the excluded values?
6 and 4.
6 and 4, okay. So if they're 6 and 4, those are our excluded values, then we're okay. Those solutions are both legitimate then, aren't they? They're not extraneous. Okay, what would have happened if one of the excluded values would have been 5, for example? Could we keep that solution? Yeah, we can't keep it. It's not part of the domain. It'd be extraneous. Okay? All right. How about,
So how are we gonna put that in the, like the answer, how would we put it?
how'd you put it in Moodle?
Yeah.
Okay, so let's look at what they're asking for here. The x values that must be excluded are, if multiple values must be excluded, separate them with commas. So in this one, we're just putting in the values. So the excluded values are what? 6 and 4. So we would just do this. We would say, in either order, in either order, we would just do 6, 4, right? The solutions are x equals, same thing. Separating with commas if multiple solutions exist. So we would just, what were they again, 5 and 8? So in either order, 5, 8. That's all they're looking for.
Did we not keep the sign?
Say it again.
Did we not keep the sign? Because it was x minus 1.
Well, yeah, but right, we're applying the zero product property, right? Remember, so we factored this, and then we're going to apply the zero product property, which means we want to know what are the zeros of each factor. Well, what's the 0 of that factor? Positive 5. 0 of that factor, positive 8. Okay? All right, last one. I'm going to, on these, I'll put a link to the textbook so you can look at some examples, but I'm not going to help you with these. Their math isn't hard. I want you to kind of have to work through how to set it up. Right, we'll go through one just to kind of give an example, but I'm going to gradually just add more and more to this category. And so they're all, I mean, they're no harder than this. They're just a little different. How could we approach something like this? If somebody's made 13 of 16 free throws for a percentage of 81.25, and here's the question. We want to know how many consecutive free throws would he have to make to raise his percentage up to 95% or higher? How would you set that up? Well, what's the unknown here? Say it again. Number of consecutive free throws he has to make in order to bring his percentage up. So that's what we're going to call the variable, right? That would be x. Okay. So then, what do? How are we going to set that up as an equation that we can solve? How do you calculate a free throw percentage? What's it mean?
That would be made free throws.
Yeah.
It's a tongue twister. So the made free throws divided by the total amount made, like.
The total number of attempts, right? So then we know he's already made 13, he's already attempted 16, but we want to know how many additional does he need to make to raise his percentage to at least 95%. So how would I write that then? How would I write the total number, including our variable x, right? The number of additional consecutive makes he needs to have, right?
So, yeah, 13 plus X.
Okay,
on
good.
top.
So that would, everybody agree that's gonna be the total, assuming he makes X in a row, starting at this point, that's the total number of makes he'd have. How many attempts?
16 plus X.
Good, and what's that have to equal?
49.
Okay, good, it's 95%, so of course we'd wanna write that as a decimal, right? So that would have to equal, and really, doesn't necessarily have to equal. Because read the question very carefully. To 95% or higher, or it might have read something like at least 95%. So it may not work out that he's ever going to have exactly 95%, because it may not fall incrementally on that. See what I'm saying? It may skip 95%.
Would we put it under or over?
So you'd have to, well, think about that. Let's just hypothetically say that if he made an additional 7 free throws, he had 95.1%.
Do that one, 'cause this is a higher.
Or higher, right? So we couldn't do 6, right? It'd have to be the one that ended up being 95 or greater. So how should I really change this equation technically to make it, strictly speaking, correct? Okay, make it an inequality. What should the inequality be? Yeah, greater than or equal to 0.95, right? And then we just solve it like we normally would, right? So if you end up with a simple one like this, what do? I mean, technically, yeah, we're multiplying both sides through by 16 plus x, but really aren't you just cross multiplying? Right, if you get a really simple ratio like that, you can just cross multiply, and that's a shortcut to what we did in that previous example, right? Okay, last one. How about something like this? This is from the test 1 from Unit 5, Chapter 8 test, essentially. Choose the graph. But there's some good stuff going on here. This is a pretty hard question. I mean, there's a lot. You've got to really, I mean, you all can do this, but it forces you to think about lots of the stuff that we've talked about throughout the year. So what do we do with something like this? We're going to choose the graph of the function. What's always our first step when we're dealing with the graph of a rational function? We want to get a sketch of that. First thing we always do.
Find the zeros.
Okay, find the zeros at the top and the bottom by factoring, presumably, right? So the bottom's pretty easy, right? What's the bottom factor into?
X plus 5, X plus 3.
Okay, what about the top? Yikes. What can we do? There is something we can do on the top.
Take out the negative 2.
We can take out a negative 2, leaving us with what?
Minus 31 X.
Okay, but that's,
Maybe minus 30.
oh, minus, you're right. Okay, so that clearly is not going to factor, is it? Right? I mean, that's a cubic polynomial factor. It would, technically, it's got 4 terms. It's got a 0 coefficient of x squared, but that's not going to factor. The only way, think back to our factoring stuff, right? The only way that we know how to factor, just directly factor, a 4-term polynomial is by grouping, and that's not going to work, right? Because the ratios don't work out. In order for us to be able to factor by grouping, we've got to be able to say that the ratio of, it'd have to be something like this. 2x cubed minus 6x squared plus x minus 3 or something, right? Where the ratio of 2 over negative 6 equals the ratio of 1 over negative 3, something like that, right? You kind of probably have seen that pattern. And if you don't, I mean, you can always just try it, but you can't do it with 3 terms anyway, right? So what are we going to do with this then? Because it's cubic, we can't use the quadratic formula. What's really our only option with this? Yeah, we got to just use the rational root theorem and just, you know, hunt and poke around for the zeros that work based on the rational root theorem, right? So let's quickly just take this opportunity to go through just a quick review of that. It's not a bad thing to review. So we're going to write out then what are our coefficients. We'll just nest this in one big list so we can make this, we can kind of abbreviate it. What are my coefficients of this cubic factor?
1, 1, 0, negative 30.
Okay, and then that's going to be the 0 column, right? That's where we got to get a 0. We'll just go through and check some stuff. So we've got factors of 30 divided by factors of 1, so it's just factors of 30. Start small, right? So we can try like 1. If I bring down the 1, 1 times 1 is 1 plus 0 is 1. 1 times 1 is 1 plus 31 is, what is that, negative 30? Is that right? Did I do that right? And then 1 times negative 30 is negative, so that's not quite going to work, is it? Right? It wanted to, but it didn't quite work. What maybe should we try though? Came pretty close. How about negative 1? So I bring down the 1. 1 times 1 is negative 1 plus 0 is negative 1. Negative 1 times negative 1 is 1 plus 31 is negative 30. Negative 1 times negative 30 is 30 plus 30 gives us our 0, right? Okay, and then we end up with what's left behind. Those are the coefficients, right? So that's going to be a quadratic trinomial with magic numbers, with easy magic numbers. It just works out to be, in other words, what does the top divide into? What does it factor into? Negative 2 times, well, but I'm writing them as factors just for a moment. So the 0 was negative 1. What's the factor that goes with that?
X plus 1.
X plus 1, good. And then we're left with the quadratic factor, x squared, what, minus x minus 30, all divided by x plus 5, x minus 3. And so I guess last step would be, we can completely factor the top. What does that last trinomial factor into? Okay, so x, say it again. Plus 5, minus 6, good. And then x plus 5, x minus 3. So we can make our list, and that list is really crucial, right? So we have the zeros of the numerator and zeros of the denominator. What are our zeros of the numerator then? Zeros of the denominator. Okay, so we do have one shared 0, right? So what does that tell us? Good. Okay, so we got a whole at negative 5. We have x-intercepts where? Okay. Negative 1 and 6. And what about the whole? Well, never mind. I won't do that. I don't want to. What about vertical asymptotes? X equals 3. Okay, so that's a lot of good information right there, isn't it? Tells us a ton of stuff. What about the end behavior? Okay, so now let's go back and look at the end behavior of this thing. So end behavior would mean What kinds of asymptotes? Horizontal, right? Or potentially slant, right? What's this one going to be and why? Horizontal? Slant. How come, Kristen?
It's a cube on the top, so the bigger factor, and there's a square on the bottom.
Okay, good. So the degree of the top is 3, the degree of the bottom is 2. When the top is 1 bigger than the bottom, it's always a slant asymptote, right? How do we find a slant asymptote?
Ratio of leading coefficients.
Say it again.
Take the ratio of leading coefficients.
Okay, that would be a horizontal asymptote, right? So let's take real briefly. Let's just hash through the 3 possibilities, right? So there's 3 things that could happen. In this case, the degree of the top is bigger than the bottom, so that's a slant asymptote. That's the one that takes quite a bit more work. That's where we have to divide it out. So we'll get back to that one. What if they're the same degree? What if that were an x cubed on the bottom? What do we do then?
Take the ratio.
Ratio of the leading coefficients, right? If you have the same degree top and bottom, we would get a horizontal asymptote with the equation y equals whatever you get, right? The ratio of the leading coefficients. What if the bottom degree is bigger than the top? Okay, then we get a horizontal asymptote at y equals 0. So just on the x-axis, right? So we got the hard one here, though. This is the one where we have to do some other stuff. We have to divide this out, right? So let's go through that. So we've got outside x squared plus 2x minus 15 dividing into negative 2x cubed. Remember, I gotta put a 0 coefficient in, right? I've got to keep a column for every power of x. So I've got a plus 0x squared plus 62x plus 60. So how many times does x squared divide into negative 2x cubed? Yes, sir.
Why don't we just factor out the x plus?
Okay, that's the other option. Okay, that's another idea. Another thing we could do is we could take this and we could cancel any like factors to make things easier too. Okay, that's the other thing. Let's go through this process and then we can look at how maybe we won't do the whole thing, but we can look at how that might have made it simpler, right? I just want to make sure everybody's comfortable with doing the long division. So real quick, what do we get then if we divide x squared into negative 2x cubed? How many times does it go? Negative 2x. Distribute that through. I get negative 2x cubed, what, minus 4x squared plus 30x. I'll subtract. Those cancel. I get what, positive 4x squared, positive 32x. You check me on this. Plus 60. Is that all look good? How about next term? X squared goes into 4x squared 4 times. Distribute that through 4x squared plus 8x minus 60. Subtract the whole thing, and we get what for our remainder? Those cancel. 32 minus 8 is what, 24? 24x, and those cancel, so we get a remainder of 24x. Okay, so then in other words, we could write this out. We could write out f of x.
Wouldn't that be 120 because
Did I mess up?
you're adding 60 because that's negative?
Oh, you're right. Okay, so it's plus 120. You're right. I wasn't really paying a lot of attention because it's not going to matter in a sense, honestly. How come? We're just going to ignore the remainder, aren't we? Essentially is what we do. Right? So we end up with f of x equals, we get the polynomial part of our answer is negative 2x plus 4, right? And then we get plus the remainder, well, with 24x plus 60 divided by our denominator, right? Okay, so have a look at this. So if that's our polynomial, right? Did I make another mistake?
Yeah.
Oh, 120. I keep doing that. Jeez. Okay, so
In the X.
up here, yeah. Okay, so then if we divide this out, right, if we simplify the quotient, that's our answer. But when we're looking at a slant asymptote, we'll ignore the rational function part of this, right? Because think about this in two ways. Think about it in terms of a limit, right? If we were to take a limit as, because that's really what we're doing at the end behavior, right? We want to know how does this thing behave when x gets really big in the positive or negative direction. As x gets really big, what's the limit of that fraction going to be? Where the bottom is a bigger degree than the top? 0, right? It's going to approach 0, and so it just goes away, and all we're left with is the polynomial part of our answer, right? So it starts to stick to the asymptote negative 2x plus 4 when that part disappears, right? When for small values of x, this part's going to be really significant. It's going to change the behavior a lot, but when you go clear out at the ends, it doesn't matter at all, right? The other thing we could think about is, and this is kind of an interesting way to look at this, we could look at f of x as having essentially two parts, just a conceptual way to, conceptualize this. You've got the yellow part, and we've got the green part. They look pretty similar. Should pick different colors. So we got the yellow and the green parts. When I have a function, f of x like this, that's a sum of two parts, really what I'm doing is I'm just combining the behaviors of those two. I'm literally adding them on top of each other, right? So this one looks like a line. What does this one look like by itself? It just looks like a horizontal asymptote at 0, right? So if I add the y values of this line to the y values of that horizontal asymptote, which are 0, they don't contribute, do they? Way out there. Either way you slice it, this part goes away, and so that's our slant asymptote, right? Okay, so now we've got just about everything we need. Right, so we got just about everything we need. We could kind of do a quick sketch of this. And what do we get? So we got vertical asymptote at 3. We get a slant asymptote at negative 2x plus 4. So that's going to be down to, let's see, down 2 over 1. So something like that. Right? Okay, you get the idea? And so now we know we've got a y-intercept. This is kind of helpful. We have y-intercepts at negative 1, so right there, and at positive 6, so that's where 3, 4, so right there. So what does this thing essentially have to look like then? I mean, if we know that it exists there, and it exists there, and it's got to stick to these asymptotes, that tells you, doesn't it? Over here, it's got to be on this side, right? It's not pinched up there. It's going to look like this. Let's see, how's that going to work? Well, it's going to do something. It could be a little bit complicated. So it's kind of doing something like that. It's going to stick to this asymptote. I'm not far enough out to graph it very well. But it's going to stick to this asymptote, and then it's going to peel off from that. And it's going to go through that point and then go down. You see what I'm saying? It'd be better if I were further away. You get the idea, though? So once again, it's sticking to this asymptote. It's going to peel off and go through that point, and then it's just going to gradually approach that asymptote. On this side over here, same kind of thing. And there's a hole. Where was the hole? Negative 5. Okay, so then clear back here. There should be a hole up there. somewhere, right? Make sense?
Yes,
Okay.
sir.
That's it?
A question.
Yep. Oh. I have no idea. I think it's Terminator.
She tried to stop the fight.
What's that? Oh, yeah, yeah.